Hi, my name is Fabian Seiler, and today I will be presenting Atomic, an automatic tool for memristive imply-based circuit-level simulation and validation. The main purpose of this tool is to drastically reduce the time spent on imply-based algorithms and their evaluation on circuit level. So let's first have a look at the typical development process, which we have shown here. In green, you can see the parts that are fully automated by this tool, and in yellow parts, they are also partially automated. The parts in red are not included for now in this tool. At first of the developing cycle, you always have the algorithm itself, so a stateful logic with a stepwise description, which then should be mapped to the topology. In the second step, we have to validate our model, so have check the logic if the stateful logic description actually returns the correct functionality. In the third step, the control logic should be generated, which is often a quite tedious task. And in the third step, the simulations should be done, which includes the energy calculation and also the deviation experiments, so non-ideality experiments of the memristor. Afterwards, a behavior level simulation can be done for different applications, and we also included the circuit level evaluation and performance metrics and a way to graphically represent the results. So let's have a look at the atomic pipeline. You can see an overview here, where in green you can see the two input files that are required to evaluate an algorithm. In red, all the different outputs that are automatically generated are shown. The first step of this algorithm is the functional validation, where either true or false is returned. And it represents if the functionality actually happens with the algorithmic steps you are described. We also return a state history for further debugging purposes. In the second step, the algorithm is mapped to the certain topology you want to use, so the different computational areas are actually called to. In the third step, you create the control logic, which are often stored in PWM files, which is often quite hard to do by hand, so we completely automated this process for common topologies. In the fourth step, the simulator is called and the energy consumption is calculated. The energy consumption is also calculated for different input combinations, and the average is also returned. In the fifth step, all the different waveforms are called and actually evaluated. We also store these to further look into the results. And then different deviation experiments are run, where we can check if the memristor, the functionality is still given if the states of the memristor change. And in the last step, we have an extensive visualization range where different outputs and results can be automatically plotted to be included in papers. But how to actually evaluate these algorithms? So you start here with a common description of a stateful logic algorithm. Then you first have to write the algorithm in a pseudocode way, which we show extensively on the GitHub. There are two functionalities. Either a false operation or imply operation is called. If no operation is called at a certain step, no operation should be written here. The numbers represent the enumeration of the used memristors at a certain topology, which is also shown more extensively on the GitHub. In the second step, we have to configure the configuration file, which gives general information about the topology, what memristors are used, and also what's the expected functionality of this algorithm. Afterwards, we just have to run the pipeline with different configurations, and we're done. That's it. Then we get these automated results, where we first have the state history plus the validation that the algorithm actually works. Then the energy consumption, which is also quite nice to have automatically. And we get different waveform deviation ranges, so we can check if the functionality of the algorithm is still given if the states of the memristor are changed, so have a little deviation in them. And we also have various customizable visualization options included. That's all. Check the GitHub and have a nice day.